Here's section 10.6, where we analyze rigid objects in equilibrium. Our objectives here are to identify the conditions necessary for static equilibrium and set up and utilize correct equations to solve equilibrium problems. Do you remember what was needed for a torque? What torque actually was? What it did? Remember, torque is the very thing that causes an object to change its rotational status. If anything is going to begin rotating or stop rotating, a torque is necessary. So we are going to establish the rules for objects that are experiencing a torque, like we did with forces, where we will start with balanced torques. Now, an easy way to think about this is to think of it like a seesaw, which you see the diagrams over here to the right. If we wanted to balance the seesaw and the masses were equal, then each person should be an equal distance away. Imagine when you were a kid, if you were going to get on the seesaw with someone that was about your same size, we'd each sit about the same distance away from the pivot point. That pivot point is now our axis of rotation. Now, if we were to change the masses of these people, like maybe have one person be twice as big as the other person, we're going to need to change their location on the seesaw. Remember, torque is equal to a force and a lever arm. If their force is twice as big, then they would have to sit at a lever arm distance that is half of what it used to be. That way, the torques will balance out. One person on this side would cause a rotation in this direction, while the other people on the other side would cause a rotation in the opposite direction. If this thing is going to be in equilibrium, we need those torques to be balanced. Otherwise, without a balanced torque, that's where we see the seesaw actually rotating in one direction or another. If there is no net torque, if they add together such that they balance out, like they would in the very top and bottom pictures here, that would mean there's no change in their rotation. This would be analogous to like equilibrium with forces. There could be several forces acting on an object, but if they all balance each other out, there won't be any acceleration. So really, there are two conditions necessary for complete equilibrium of an object. It would be the translational piece, where the sum of the forces is equal to 0, and the rotational piece, where the sum of the torques is also equal to 0. That's how we define static equilibrium, that in these conditions, a static equilibrium would result in an object that is at rest. It has no translational or angular speed, meaning that the velocity of the center of mass is 0 and omega is equal to 0. Now, is this the only kind of equilibrium? Absolutely not. Remember, equilibrium is saying that the forces are balanced and there's no change in the rotation or translational motion of the object. That means that something could be moving with a constant velocity as well, or a constant omega. Here we're going to be looking at static equilibrium examples. Now, in a complex system involving several forces in many directions, you really would have 6 different equilibrium equations. You would have the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the forces in the z direction, all equaling 0, so that again there is no acceleration in the x, y, or z direction. We would also have 3 equations for the rotational status of that object. For complete equilibrium, again, the sum of the torques is going to have to be equal to 0. But we're looking at the sum of the torques around an x-axis of possible rotation, the sum of the torques around a possible y-axis of rotation, and the sum of the torques around a possible z-axis of rotation. All of those having to equal 0. Now, when we look at these 6 equations, all having to equal 0, and you think about setting up 6 different equations to solve a single problem, it does seem a bit excessive. That's how it would work if you were working in all 3 dimensions. But what we're going to do to simplify our work a little bit is we're going to restrict our analyses to situations where the forces are coplanar, meaning that they all lie in the same plane. So if we had just an xy plane, we could set this up and look at all the forces being within this plane, and therefore the only axis of rotation being a z-axis that would be coming in or out of the page. That actually drops off half of these equations, so that we no longer have to look at forces in a z direction. We no longer have to look at torques around an x or a y direction, and we're down to only 3 equations now, which is going to be much more manageable. Make sure that you recognize that in these problems, it's important to find all of the external forces acting. If you don't recognize all of those forces, your analysis will be wrong because you will be missing some of those pieces. So just like in force problems where you spend maybe the majority of your time or a good chunk of the beginning of your time in solving a problem as looking for those forces and identifying what's there, you're going to do the same kind of things in these problems here. Let's check out an example where we're using those 3 equations to solve a problem. Here we have a uniform horizontal beam. It's 8 meters long and is 200 newtons. It's attached to the wall by a pin. We can see this connection point right over here. At that connection point, there's going to be a force from the wall that's pushing out on the beam and sort of supporting it upwards. There's some sort of a force there that we don't really know exactly what direction it's in, but we're going to call that force R as sort of a contact force there. Now on the far end of the beam, it's supported by a cable. Now of course there's a tension force here through the cable. It's connected at a 53-degree angle. We also know that there is a 200 Newton man that's standing on the beam 2 meters from the wall, and we want to find the tension in that cable and the force exerted by the wall on the beam at that pivot point. So we've already labeled 2 of the forces in our diagram here, but there are a couple more. Acting from the center of mass of this beam, there's the weight of the beam itself, that 200 Newton force. And there's also a weight from the man pushing down on the beam in his location, which would be a 600 Newton force. So we've diagrammed all of our forces acting on this system here, and we're now ready to start looking at our equations. Remember, our equations are 3. There is the sum of the forces in the x direction, and we'll maybe start with that. In the x direction, we know that we have a couple of components, and actually let's zoom in here and see some of those components maybe a little bit more clearly. We'll put them in a new color so that it's easier to see those components. So basically there's 2 values here that need to be broken down into components. It's the r value and the t. Now for the r value, we would have this component here. So some of the force from the wall is pushing outward on the beam, and that would be a component that we could write down as maybe an r sine of theta or an r cosine of theta. If we call this angle here a theta angle, then this piece here would be an r cosine of theta. And there's also the component of the r force that's going in an upward direction. This would be the r sine of theta value. The tension force also needs to be broken down into components. We have this piece here, which would be our tension force times the cosine of 53 degrees. And we would also have the y component of that tension force, which we could then write as t sine of 53 degrees. So now that we have these pieces broken down into components, it's going to be easier to go back to our equations and sum up all the forces in the x and the y directions. In fact, if we were to look at the x direction, we'd see that we really only have this component of the r force here and this component of the t force over here. So in our x direction, we could write down our sum of the forces as an r cosine of theta minus a t cosine of 53. And that would have to be equal to 0 if we were in equilibrium. Now if we look at the y direction, in the y direction, going upwards, we have the r sine of theta. We also have the t sine of 53. And going downwards, we have the 600 Newton man and the 200 Newton beam. All of those having to be set equal to 0 as well. Our third equation
would be an equation based off of torque. So here's where some of our new stuff is coming in. When we talk about torque, we have to choose a pivot point for that torque, or a point of rotation. In this case, there is a point that would be a wise choice, and the reason why it would be a wise choice is because this choice is going to result in the least variables in our equation. It's a point that kind of makes sense because if we choose this pivot point here at the wall, that's going to be a spot where we now eliminate the R variable as creating any torque, because that R variable is now not going to have any lever arm to it. So when we think of torques as a force times a lever arm, the R force has no lever arm and therefore cannot contribute to the torque in any way. That would mean that we really only have to look at the 600 Newton man exerting a torque, the 200 Newton force from the weight of the beam exerting a torque, and the perpendicular component of tension creating a torque. Now remember what we said about directions on torque, that anything that would cause something to move in a clockwise direction is going to be considered a negative torque. So the only thing here that would cause this to move in a positive direction would be the tension force, or that component of the tension being the T sine of 53, acting at a lever arm of 8 meters away. That would create counterclockwise rotation and therefore positive torque. Negative torques would come in with the 600 Newton man exerting a torque at his position of 2 meters away from the pivot point, and also a negative torque coming from the 200 Newton bar at its position, which would be the center of mass of the bar, so a position of 4 meters away from the pivot point. We now have all three of our equations set up. If you'd like to pause the video and see if you can utilize your algebra skills to solve this, go ahead and pause it now. I'll run through a few brief things here to show you what that solution would be. Now, in the first place, our tension or our torque equation as it is already ready to be solved. Notice that there is only one variable in this equation. If you were to take the time when you pause this video to actually solve for that, you would have found that the tension force is equal to 313 newtons. If tension is equal to 313 newtons, now we can come back to some of our other equations and plug that in. For example, we can plug that value in here, and we can also plug that value in here, meaning that we are left with two simplified equations where we would have our R cosine of theta equaling 188 when we plug in what t is equal to, and our R sine of theta equaling 550. Again, I got each of these numbers here by simply plugging in t and simplifying these equations that I have here for the sum of the forces in the x and the y directions. Now that I have these two equations, I could solve for any one of those variables. For example, solve for the r in the second equation, where r would, or in the first equation, where r would be equal to 188 over the cosine of theta. I could now plug this in to my second equation and solve from there. What you'd find is that you'd get theta equal to 71.1 degrees, and you'd find that force R equal to 581 newtons. We are now left with everything that we wanted. We wanted the tension force, and we wanted the force exerted by the wall. The wall was 581 newtons at an angle of 71.7 degrees from the horizontal.